All right, let's make some support vector machines. And we're going to use these artificial data sets that are just dots in a graph so we can practice sorting them into categories. So I'm going to paste this. All right, this is going to make random blobs. There is a function in SecML, the library, to make random blobs with setters and standard deviation of your choice. We'll have 100 training sets and 25 test set samples, and then plot them so we can see what they look like. All right, there it is, downloading some required libraries. There we are. Now I get the plot. Okay, so I got a bunch of blue dots over here and a bunch of red dots over there, and there's no actual overlap. You could draw a line here and have 100% division between the two. So this will create a scalar support vector machine model and fit it using standard fitting techniques, and then just give us some measures of how well it performs. So I copy that and make another block of code here. All right. Notice it runs very fast. There's really very little mathematics required to do this. It just has to find a line and then maximize the width of the street. And that's the consequence. Now we're going to expand the y-axis by 100. So this just takes the old x values and expands it to 100 times the previous value. And that's going to create a biased set of data, which it looks exactly the same, and the intuitive answer would be a line going through the same place, but the y-axis is now in bigger, the vertical axis, I should call it probably, because it's technically an x, it's an input variable. But anyway, the vertical axis is now in a scale that gives it values that are 100 times bigger, and that means we're going to count vertical distances as 100 times more important than horizontal distances, and that's going to mean the optimal solution is now here, because we're not willing to accept a larger vertical error. We're willing to accept large horizontal errors, but not vertical errors. So that's the narrowest street on this scale, and that's going to be a common problem. And so then the next thing is to do soft margins to handle more realistic data that cannot be 100% split in two pieces. So we just move the standard deviation of the clusters so they'll overlap some now. By the way, in these things, when you do random blobs, a lot of these, you specify the seed. I don't see it in this one, but if you specify the seed, then you'll get exactly my answer. And that seems to be the case here. Notice this pattern looks sort of like a C, and those three in straight line. You're getting exactly the same blobs. So I should be able to find, here it is, random state equals 999. This is an important thing to know. The randomness we're using, these are pseudo-random numbers. They're not really high-quality random numbers. And you can, if you specify the state, they're completely predictable. So this is something I do for projects when I want to have a scoring engine. That means you will not just get random stuff, you'll get exactly the same random numbers I got. So at the end, you'll get exactly the same values for things like performance and such. So now we create and train a model. And don't know if I got my copy to work. All right. And so this is going to be a class of scalar vector machine here, but it's going to have this parameter C, which is a regularization parameter. And we're just going to try various values separated by powers of 10, 0.0001, 0.001, 0.1, 0.1, and 1. So we'll try various degrees of regularization. Somehow my copy and paste is not working. Let's try it again. There we go. All right. Once again, it runs very fast. There are not very many calculations required here. And so there's the C of 0001. It's a complete failure. It classifies everything as blue. Here's 2 zeros and 1. Again, the regularization is somehow shoving it way over to the side. Here's a pretty good solution, 0.001. That looks reasonable. And 0.1 is about the same. And 1 is also about the same. So there's a wide range of regularization parameters to give you a similar solution looking pretty good. All right. And now if you want to do the curved data set, then you have this. And so to create and train the model, you can see the model. I guess I'll keep doing these live because it is pretty informative. So here's a curved data set. Let me just make a new notebook here. I think that'll be fine. I want to move to trash, return to Colab, new notebook. All right, so I put in this code. And it calls this thing called make moons, which creates data that's not just a simple Gaussian distribution, but these curved distributions. So you can practice working on them. So now we create and train a model with a polynomial fit, which can fit it uses polynomials, it uses powers of x1 and x2 to make new features so that it can fit curves. And I still have to use the keyboard to paste. Still is not working. There we go. All right. Again, and so here's what it's going to do. It calculates polynomial features, so it adds more dimensions of x1 squared, x1 cubed, x1 to the fourth, and so on. Then it runs it through a scalar because those are now different sizes. So it's going to rescale them to avoid the problem we saw last time where one parameter is larger than another. And then it's going to run a linear support vector machine through this higher dimensional model that has powers of the input axes of the input data there as dimensions. And so now this will show the result. And there's the result. This curvy decision boundary is actually a straight line in that higher dimensional space caused by adding more polynomial features. All right. And so then you can do the same thing with a polynomial kernel, where it's included in the calculation without having to separately create those features. And here's an example of a 10th degree fit. So that's where you get to practice these support vector machines. And I'll stop this video. There's the button I have trouble finding.